Good morning and welcome to this session. In this session we are going to see some important functions that require to solve ordinary differential equations. The first function is Heaviside unit step function and second one is Dirac Delta function. In this session we will discuss importance of Heaviside and Dirac Delta functions, formal definition, diffusing multiple valued functions using unit step function, and the relationship between Heaviside unit step function with other engineering functions of importance. First of all, we are going to discuss why these functions are very much important. The first thing is wide range of utility due to high representation power. The second point is help to model real-world problems to mathematical model. And third one is a popular preprocessor for engineering functions in integral transform analysis. In nutshell, we can say that mathematics and engineering is moving in different direction. Mathematics is basically working on some concrete definition of functions, but engineering as a doing science, we start from real problems or real world problems and come into mathematical structure. And so the representation of real world problem into mathematical form demands lot of special functions. Such two important functions are Heaviside unit step function and Dirac Delta function. First of all, we are going to discuss the Heaviside unit step function. The Heaviside step function or the unit step function, usually denoted by h or u or sometimes theta, is a discontinuous function. It is named after Oliver Heaviside, whose value is 0 for negative arguments and 1 for positive arguments. That means these functions gives response 1 for positive arguments. It gives 0 for negative arguments. It is like positive thinking. Whatever you see is positive, we give importance to everything, as equal importance to everything. If you see some negative, you completely discard it. That means assign 0 value to that. Such a good qualitative and both quantitative function is a Heaviside step function. In mathematics, the unit step function is denoted by u of t minus a, where t is our variable, a is called the threshold. A formal definition of Heaviside step function or unit step function is like this. If t minus a is positive, it gives 1. If t minus a is negative, it is 0. We formulate this as a two-case function like this. Now look into the range. If t greater than or equal to a, what happened to t minus a? If t is greater than or equal to a, t minus a is positive. In that case, the response is 0. If t is less than a, definitely t minus a is negative. In that case, it gives 0. That means whatever positive values give to u, it gives plus 1 as response. If you put negative values to u, it gives 0. That's all. And here the value of t minus a is positive or negative depending on this a, and so this a is called the threshold. Using this figure, I will show how this function is called a step function, because this blue graph gives the plot for u of t minus a with a is equal to 1. If a is equal to 1 and beyond 1, it gives the value 1. And below this one, it gives 0. So it creates a single step of height, this 1, height 1, and so it is called a unit step function. Now for an example, I consider mathematical representation of a stabilizer. Consider this mathematical function sz of v is equal to 230 into u of v minus 230. Here we have the unit step function, so look into the argument. When this v minus 230 is positive, this u gives 1 response or 1 output. If v minus 230 is negative, it gives 0. That means sz of v is 0. Now this 230 is our home voltage or home potential difference. In that case, if the home potential difference or voltage is greater than or equal to 230, this u of v minus 230 gives 1. So it is stabilized as 230 into 1 or 230 volt. If the voltage is less than 230, v minus 230 is negative. In that case, this u of v minus 230 is 0. So the stabilizer gives the output 0. That means it cut off when this voltage is less than 230. So a voltage stabilizer can be represented mathematically like this. Such functions or some special functions are extensively used in engineering and applications. Now, diffusing multi-valued functions using step function. This is one of the important application of unit step function in application viewpoint. First of all, consider this function f of t. It has two values 0 and t depending on its range of t. If t is in between 0 and 3, it gives 0. If t is greater than or equal to 3, it gives t. So this function gives two values 0 and t depending on the range of t. Now we are going to diffuse this function together and put it a single line definition. Now look into the definition and how to write this f of t. First of all, write the basic definition. That basic definition is 0 or initial definition is 0. So 0 plus. Now take the difference of these values t minus 0. T minus 0 into u of this t minus 3. Here higher value is t. So subtract from t u of t minus 3. Once again, start the base value 0 plus take the difference of the responses t minus 0 into u of t minus 3. So a multi-valued function can be combined into a single valued function with the help of unit step function. These two ranges will be accommodated within this unit step function. That is the advantage of using unit step function along with multi-valued functions. So we consider a more lengthy problem. This function f of t has three definitions, namely 2, t square by 2 and cos t. These are the outputs. These outputs depending on the range. When 0 is less than t less than 1, it gives 2. 1 less than t less than pi by 2 range, it gives t square by 2. When t exceeds pi by 2, it gives the value cos t. As in the previous case, we guess how we can write this function f of t using unit step function. So f of t is equal to base value 2 plus t square by 2 minus 2 into u of this t minus 1 plus cos t minus t square by 2 into u of t minus pi by 2. That is base value 2 plus difference between these two responses t square by 2 minus 2 into u of, here t is higher, t minus 1 plus cos t minus t square by 2. Next difference is cos t minus t square by 2 into u of t minus pi by 2. U of t minus pi by 2. That's all. So we can combine this function f of t using unit step function like this. So unit step function is a powerful tool to combine or diffuse different definitions of the function in a single line. There are many other form of diffusing using unit step function. Instead of this, we can use different combination of this t using unit step function. It is possible, but I simply give an easy method to rewrite this function using unit step function. I repeat, start with the base definition, that is 2 plus t square by 2 minus 2 difference of responses into u of t minus 1 plus next difference cos t minus t square by 2 into u of t minus pi by 2. That's all. We can apply this method to a function with any number of subdivisions or any number of multiple values depending on the range. One thing you have to remember, this function f of t doesn't takes multiple values simultaneously. It takes different values in different range. Otherwise the definition of function will lose. A function has a unique definition, a unique response or unique image corresponding to different values of its input variable. Here this function take unique values, but these unique values are different depending on the range. That is very important. So another example, consider this function f of t. This is a double valued function depending on the range. Now we are going to diffuse it together using unit step function. So answer, we can guess the answer like this: f of t is equal to base value 10 sin 2t plus 0 minus 10 sin 2t into u of t minus pi. Then we can verify this. It's correct. 10 sin 2t plus 0 minus 10 sin 2t into u of t minus pi. So in this way we can combine or diffuse or fuse together multi-valued functions into a single line function. Now we are going to discuss the second popular and important discontinuous function. Its name is Dirac's Delta function or unit impulse function. This discontinuous function was actually proposed by the Nobel Prize winner quantum physicist Paul A.M. Dirac, and who had submitted the first ever research thesis in quantum mechanics. And one more thing, this great personality was a professor in Lucasian mathematics in University of Miami, and so we are very much excited to see his results and see his paper in research journals or somewhere else in the internet. Okay, to model the Dirac delta function, he make use of another function that is called an impulse function or a short time impulse function, and that function is defined like this: fk of t minus a is equal to 1 by k when t is between a and a plus k and 0 otherwise. When we look into this function, if this k is larger and larger, this interval becomes larger and larger. In that case, this 1 by k becomes very small and goes to 0. That's all. If k is very small, then it is an interesting case. That means the time gap is very small. That means the action is happened for a very short time. Then k is very small, and so 1 by k is very large. That means it represents a function that is acting for a very short time if k is very small, and that is why it is called an impulse force. And so it's a short time force or impulse force function when k is very small. Actually, Dirac delta function is this function, this short time force function with the k tends to 0. When k tends to infinity, k tends to 0. Okay, when k tends to 0, this time becomes very large, becomes infinity. It is similar to many contexts we are using this thing. Even in music, we called velli. This velli is actually an abrupt change in the rhythm. If the rhythm or the harmony of that vocal sound changes abruptly, then it is called a velli. That velli is actually a white noise, and white noise can be represented by this Dirac delta function. And many application, impulse force, hammer blow, a very high force or a very high force acting for a short time, everything can be represented using this Dirac delta function. So we are going to define this Dirac delta function formally. So Dirac delta function is delta of t minus a. We simply mimic the structure of delta of t minus a from u of t minus a. Delta of t minus a is equal to infinity when t is equal to a. When this t is equal to a, then t minus a it becomes 0. So time difference is very small, then its action should be very high. That means the response should be very high value, that is infinity. If it is not t is equal to a, that means t is different from a, from the fixed point a, then automatically it has no impact, it is 0. That is the impulse. And one more thing, that if we have to, this function delta of t minus a should have to satisfy this property: integral 0 to infinity delta of t minus a dt is equal to 1. The left side integral is familiar to the people from engineering mechanics, and it is nothing but the impulse of that force, and it can be represented as, or it can be interpreted as, the impulse should be 1. That is why it is called unit impulse function. This Dirac delta function has also another name, that is unit impulse function, because of this constraint. When we look into the graph, it is the discrete case of Dirac delta function. I keep 1 as infinity here. In order to represent this in a figure, I put 1 as infinity. When this a is equal to 1, then automatically what happened? Delta of t minus 1, that becomes 0. T minus 1 0 here when t is equal to 1. At that time it will give the highest value, the peak value, that goes to infinity. Actually it is very high. That means it has only one value, that is relatively very large compared to other values. Other values are 0, and this situation is called an impulse or white noise, and it is represented by Dirac delta function. Now we discuss relationship between other popular functions. It is very much interesting. Even in the advanced topics, even in applications of mathematics and engineering, that is artificial intelligence and machine learning, we extensively make use of some versions of these special functions. The special function in terms of the special functions in applicability. The one thing is Heaviside step function is the derivative of the ramp function. This ramp function is defined as r of x equal to maximum x comma 0, and this is popularly known as rectified linear units, rectified linear units in deep learning. Because when we take this ReLU as activation function, then its derivative in backpropagation we have to take the derivative of this activation function, then that derivative will become 1 because its value is maximum of x comma 0. When we take derivative with respect to x, it gives 1 for the ramp value. That means it is unit derivative, and that derivative is Heaviside's unit value, that is the Heaviside step function. That is the relationship between Heaviside step function and this ramp function or rectified linear units in our deep learning mechanism. The second important property is Heaviside step function is the integral of Dirac Delta function. That is important connection. That means Heaviside step function can be calculated using integral of this Dirac Delta function. So this is a calculus relationship between Heaviside and Dirac functions. Next is sigmoid function or logistic function. The sigmoid function is also one of the important activation function in deep learning, because we are using the sigmoid function in binary classification models, and this sigmoid function is actually the smoothed version of Heaviside step function. So this sigmoid function can be generated using generated using with the help of smoothing this Heaviside step function. Another interesting relationship between a Dirac Delta function and Heaviside function is the Dirac Delta function is considered as the distributional derivative of Heaviside step function. The distributive derivative is not in the sense of the classical differentiation. It is happening only in some intervals. Some special type of treatment we are applying in the case of distributional operation and distributional calculus. And so Heaviside step function, if we consider Heaviside step function, and when we take the derivative, then we automate distributional derivative, we get the Dirac Delta function. So this wonderful relationship between this Dirac Delta function and Heaviside step function is make use of this Laplace transform and also Fourier transform. Then the applications of these popular functions, both Heaviside unit function and Dirac Delta functions have crucial role in representing dynamic systems that we are already discussed. Such systems or dynamic systems can be represented using ordinary differential equation, and so these two functions has crucial role in solving ODE using Laplace transform or Fourier transform. That is one of the important use of Dirac Delta function and our Heaviside unit step function to combine multi-valued function and also to use with ordinary differential equation. So that is all about these basics of Heaviside and Dirac Delta function. We need these functions and its properties in Laplace transform. That is why we released this video lesson in advance to this solution of ordinary differential equation using Laplace transform. Thank you very much for the patient listening.